So, welcome back to the wonderful world of acids and bases. Isn't it fun? Aren't you having such a good time? So, up to this point, we've talked about electronegativity and size, and I know that you're excited to talk about the next grouping that we can relate to acids and bases. And the next grouping is something that we are going to call substituents. And substituents are just groups that are what we call attached. Okay, well, what are they attached to? They're attached to what we call the main chain. And this is a term that we're going to be using over and over throughout the semester. So basically, the way that I want you to think of this is, let's say that the major part of the molecule is right here. Substituents, or these groups, are going to be hanging off of this chain. And it's going to be a little tiny piece here and maybe a little tiny piece there or something like that. But the majority of the compound is here, the way that I've drawn it, in the center all the way across from left to right. And we get these little groups that just kind of hang off to the sides. Well, it's those groups that we're going to be focused on, because these groups do play a role in the compound's acidity in the world of acid and base. So we've got to talk about why. Why do these groups, and not all the groups, but why do these groups play a role, and how on earth can this actually go forward? And how does it affect the acidity? Does it increase the acidity? Does it decrease the acidity? What's going to happen? So again, we are focused on hydrogens. We're focused on the hydrogen activity and what goes on as far as donating a hydrogen to solution. If this molecule can donate hydrogen very easily, then this is a better acid. And if it doesn't want to give up that hydrogen, then it's a weaker acid. And these substituent groups, these groups that are hanging off of the main part of the molecule, can play a role in those particular types of activities. So on this slide, you're basically seeing the word substituents up here, and I just want you to keep in mind that it's a fancy word. It's a word that we use to make us sound smart, and the only thing it means is an attachment. That's all that it is. And I told you that not all the groups are going to play a role, right? So the groups that do play a role are groups that have electronegativity values. So these are groups like fluorine or chlorine or maybe oxygen. Anything that's nestled around the fluorine on the periodic table will have high electronegativity values. And these really do play a major role in affecting the acidity of a molecule if they are attached as substituents. So we'll take a look at some examples. We'll see what they do. But these are the particular types of groups that we're going to be looking at. So electronegative groups or electronegative atoms. If you do have electronegativity, keep in mind the definition. I always say it over and over because I don't think that you can hear it enough. But electronegativity is electron greedy. That's what this means. So if we have a group that is electron greedy attached to the main part of the molecule, it does play a role and a factor in how this molecule gives off the hydrogen. Okay? All right, so not only the type of substituent is going to be important, but also the position of that particular type of substituent will be important as well. So what do we mean by this? Okay, so the best way that I can describe this is show you an example and talk through the example, and then you'll get to see what we're really referring to when we say type and position. All right, so here's an example. And up here at the top, you're going to see a group of atoms that are making a molecule, and they are very similar all the way across the board. CH3COOH. That's acetic acid right there, okay? And the pKa of acetic acid is 4.76. So if you take a look at what they've done in all of the other corresponding structures that are beside of that, they have replaced one of these hydrogens here with here a bromine, and there a chlorine, and here a fluorine. So the reason that they did that is because we want to compare and contrast yet again. And we want to see what happens to the pKa values as we place these groups on there. So keep in mind, once more, fluorine has the highest electronegativity value. And as I go away from it to the left, and as I go away from it down below, that electronegativity value goes lower and lower and lower. So what we've done in this example is we've replaced a hydrogen with a bromine group. And that bromine atom is going to be attached to this molecule. And if you notice, this is the hydrogen that's going to get removed, right? If this thing behaves as an acid, it's that hydrogen that's going to disappear on us. That's the donor. So this bromine is on a carbon, and that is neighboring the carbon that has the OH group on it, and that H is what's going to get removed. So the bromine does have electronegativity value on it. The bromine, therefore, is electron greedy. So the bromine is sucking electrons toward it when it can. And because it's electron greedy, because it's an electron sucker, then this hydrogen bond becomes very weak. And this can easily be removed compared to a group that doesn't have anything electronegative on it. Notice that the pKa plummets here. It goes to 2.86 from 4.76. So this almost gets cut in half, right? So that electronegative atom plays a major role in how acidic this molecule is becoming. Well, if we replace that with a higher electronegativity group, this is still an electron sucker, and you're still seeing it pull electrons toward it. And this chlorine, again, is right here beside of that neighboring carbon. This hydrogen can be removed even easier. And that's because chlorine has a higher electronegativity than bromine does. And then, of course, fluorine has the highest of them all. So this is a super electron puller. It really is going to pull as much as it can toward itself. And when it does that, that hydrogen is even easier to remove, and that makes this pKa go even lower, so it becomes a better acid to begin with. So what you're seeing here in this bottom diagram are these arrows, and these arrows are pointing you in the direction of what's happening here, right? So here's the bromine that's on that carbon. They've just drawn it a little bit different. Up here at the top, they drew it down, and here at the bottom structure, they've drawn it to the left. So this is the same structure. It's no big deal. But notice the arrow flow. They're showing you that bromine is pulling electrons through the molecule and getting them away from that hydrogen that was acidic in the first place. And it just promotes that hydrogen to leave even more so than what it was. And we do have a proper term for this. We don't call it bromine is sucking electrons through. What we call it is inductive electron withdrawal. I just think sucking electrons through is a little bit easier to say, but the proper term is called inductive electron withdrawal. All right, so that is the process that these electronegative groups will do when they get slapped onto molecules like this one that are behaving as acids. Well, those are the types, right? So we compare different types of electronegative atoms here: bromine, chlorine, fluorine, and then one with nothing at all. But we also said that size or location was also part of that argument as well. So what you're seeing here is a similar structure, but it's a little bit longer on this side. You know, in the other example, this just kind of ended with a CH3. So this one has a couple of extra carbons, no big deal, but they did that for a reason, because they're getting ready to show you what happens when they take an electronegative atom like bromine and just kind of shift it on down and then measure the acidity, and then shift it down, measure the acidity, shift it down, measure the acidity. And that's what these examples are basically showing you here. So here we have a molecule. This hydrogen is removable. That is a carboxylic acid group. We know those pKa's are about 4.76 in total. So there is a donatable hydrogen here. And we have a bromine atom that's on that carbon. So this bromine is electron sucking through the molecule, electron or inductive withdrawal, right? So it's pulling electrons through. This is easier to donate because of that reason, and this pKa is a 2.97. Well, if we take that bromine and we just shift it a little bit further away, and we get it further away from that hydrogen, this bromine's still going to suck electrons through, but the presence of that bromine is not as dramatic. So it's further away from the area that's getting donated, and because of that, it doesn't have as much of an effect as it did before. And we see that this molecule is not as acidic as the previous one, and therefore the pKa goes up. Again, remember, this is kind of like the pH scale. The higher the pKa, think of it as more basic. And that's what we have become. It's still an acid though, right? pKa of 4, it's still acidic, but it's more of a base and less of an acid compared to the first one. That's what we're always doing. We're always comparing them here. Well, if we take that bromine and we shift it yet again, one more carbon to the left, we get further away from that OH group. If we get further away from that hydrogen, then this has less of an impact as far as electronegativity goes and inductive electron withdrawal goes. So therefore, this molecule becomes more of a base and less of an acid compared to the previous one. Okay? And then finally, here at the very end, we take the bromine and we move it one more spot left-handed. And as you can imagine, moving it even further away from the OH group is going to not have a major impact on the acidity of that hydrogen like it did before. Therefore, it is less of an acid compared to the previous versions. And this pKa is even higher now, and that's 4.71. So, the type of electronegative atom that goes on to these groups are going to play a role, and that affects the acidity of the molecule. And then the location of that particular type of atom will also play a role in the acidity of that type of molecule. So the types of questions that you're going to see from this, and the types of things that they like to ask, are questions like this. And it will say, which one of these are stronger? They don't really want you to look up a chart. They don't want you to go to Google. They don't want you to get pKa values. They want you to look at structures and just simply based on the structure alone, tell me which one's stronger. Because folks, when you start doing these assignments and when you start doing the test, you might not have those resources available to you depending on the type of test that you're given. Especially if it's a one where they want you to use something about its structure in order to determine which one's a better acid, which one's a better base, and so forth. So we're going to start with part A. And part A, I've got two choices. I've got either this one or I've got this one. And I've got to figure out which one is the better acid, which means which one of these would donate the hydrogen better. That's what we're after here. Okay, so if we look at the differences, it looks like the major difference is this oxygen. In this molecule, they cram an oxygen right here, kind of in the center, kind of, right? And then over on the right-hand side, there is no extra oxygen. Okay, it's just all carbons and hydrogens. So the donatable hydrogen is right here on the end. That's where my alcohol group is at, my OH. And I want to know which one of these would release that hydrogen a little bit better, because that one's going to be my stronger acid. Well, because this one has an oxygen, and because this oxygen is electronegative, and this one does not have one, it's just all carbons and hydrogens, I'm going to get some electron pull through the molecule here, and that oxygen is going to start sucking up some of those electrons, and it's going to start weakening that bond with the donatable hydrogen, and this hydrogen can be released a little bit better. So which is the stronger acid? Folks, it's going to be this first one, and that's because it has the presence of oxygen, which is electronegative. Okay? Now for part B, we also have two choices. If we look at the major differences here, I see a fluorine right here, but you know, I see the fluorine right there as well, and that position's not changing. It's the same in both. And I have two on the left and I also have two on the right. So this is not really what they want me to focus on here. They're trying to trick me is what they're trying to do. So if I look on the very end, this is where the differences occur on those particular types of molecules. Well, with these particular differences, I have a nitrogen and I have an oxygen. So if we use the rule that we just talked about, okay, which one is more electronegative? Is it nitrogen or is it oxygen? Okay, well, if I pull up the periodic table here, Here is N and here is O. So oxygen is more electronegative, therefore this is a better electron puller through the molecule. And because it's a better electron puller, then these hydrogens are going to have weaker bonds. So therefore this molecule is probably going to be my better acid. But folks, we could have answered this question in a different way, all right? The way that we could have answered this question is not even worry about any of that mess. We could have easily looked at this and said, this is a protonated amine, this is a protonated alcohol, and we've already learned some key pKa values. And those pKa values, we learned of alcohols and amines, carboxylic acids, and protonated species. And here were two of them. And on that chart, it shows protonated alcohols are better acids with lower pKa values than protonated amines, right? So we could have used that justification as well to answer this question. No big deal. They're telling us the same story, so that's good. Part C, again, we've got two different groups. If I look at the differences here, the OH group here on the end, and then it looks like 1, 2, 3 carbons over to the left, I have an O. And then on this one, 1, 2 carbons to the left, I have an O. So out of these two choices, we know that the position of the O is different. This is the electronegative atom, and this is my electron puller. So in this example, to the right-hand side, the oxygen is closer to the acidic hydrogen that we are focused in on here at the very end. So because this is closer, it has a better effect on that hydrogen. It pulls electrons away from that hydrogen a little bit more than the structure to the left of it. So this one is going to be the stronger acid, the one to the right-hand side. Finally, part D, here we see OH, and there we see OH, and then beside of that we see a carbon double bond O, and then beside of this one we do not see that. That double bond O is shifted down one more carbon, so it's further away from the hydrogen that can be donated here. Now, you might be asking, how on earth do I know which hydrogen's getting donated? Well, folks, keep in mind, anytime I told you that hydrogen is connected to a carbon in 3s or 2s, you get rid of those. These are not going to be acidic. So this is the only hydrogen possibility that I could even pick from. And the other examples are the same way. Look up here at part C. 3 hydrogens to there, 2 hydrogens to that carbon, 2 to that carbon, 2 to that carbon. The only hydrogen that I have to pick from is that hydrogen on the very end right there. Okay, so D, there's my acidic hydrogen on the end. Here's my electron withdrawing group. This is my electronegativity atom. And this one is closer to that hydrogen than this one is. So because of that, this pulls the electrons up in more force, and it affects that bond better, and therefore it weakens that hydrogen bond. So this one is a better acid than the one to the left. And again, it's all due because that electronegative atom is on or closer to that more acidic hydrogen on the end of the molecule. All right. Okay, so that's the story with size and position, folks, and that is really what this thing is going to be about. If you look at some of the other examples in the textbook, you might see an example like this, and it will say rank them. So 1, 2, 3, 4, because they give us 4 structures. Which one's the strongest and which one's the weakest? Well, this one to the left is going to be our strongest because we have 2 fluorines, 2 groups, and the rest of them just have 1 or none. And this one that doesn't have any kind of group, that one's going to be our last one. So there's 1 and there's 4. Now we've got to kind of compare these two with each other. The acidic hydrogen is here on the very end. This fluorine is further away than this one. So my first choice with 2 of them, that's the best acid. And then the last choice, where fluorine is the closest to that hydrogen, is my second. Then this one with fluorine further away is going to be number 3. And then finally this one with no fluorines at all, no electron pullers, that will be the weakest acid of the 4 that are pictured. But yet again, this is still an acid. Okay, I don't want you to get confused with that. It's still acidic. It will still donate its proton. No big deal here. But we are ranking these acids in terms of strongest to weakest because we are still terming them as an acid. All right? Do not let that get you confused. Finally, here's another example, and it will say which one is the stronger base. So yet again, what I would like for you to do is to go through and rewrite this question that you can feel comfortable with. So what we do whenever we see base, strong base means weak acid. Which one of these is the weakest acid? That is what they're after. So anytime you see these negatives, that is where the hydrogen was. Okay, so I'm going to write these, they're bases the way they're represented right now, but I'm going to write these as acids. So I'm going to put the hydrogen on there. And now everything is in terms of an acid. We have acidic structures, and we can go through and make the same determination as if we were thinking about bases. So which is the weak acid? Well, bromine and fluorine are substituents. Fluorine is more electronegative. It's a better electron puller. That means that this is the strongest acid out of the two, which means this is the weakest acid out of the two. Here, the difference is the chlorine position. Chlorine is closer to that hydrogen here, and chlorine is further away from that hydrogen in this first example. Because this is closer to that hydrogen, this one's going to be the strongest acid, which means that this one is the weaker acid, or stronger base. Means the same thing. For part C, here I have a bromine, and here I don't really have anything extra. Okay, the double bond O is there, but the double bond O is here as well. That's the same in both structures. That's not really going to play a major difference here. But this one has a bromine and this one does not. So because this one has a bromine, it has an electron puller, this one's going to be a better acid, a stronger acid, which means that this one is going to be the weaker one. And then finally D, down here at the bottom, I see the double bond O further away from that hydrogen than in this second example here. The double bond O is closer. So the double bond O is closer to that hydrogen, which means that this is the strongest acid, which means that this is the weaker acid. So again, you have to read these questions carefully. If not, they're going to trick you up. And they're going to trick you up most of the time in the acid-base world when they start asking about bases, because they know that most people feel uncomfortable with this because as instructors, we talk about acids all the time. But yet again, force the rules to play your game. And your game is to compare acids. So rewrite these questions. No one says that you can't do that in your head. Rewrite the questions to make it comfortable for you. And the only thing we have to do is change the word stronger base to weaker acid, and then we've got it. That's all that matters. Okay? So that's where I'm going to stop this video. In the next video, we're going to move on, and we're going to talk about a topic called delocalization. Delocalization is also one of these terms that we're going to be talking a lot about throughout the semester. We want to go ahead and introduce it so that way we'll get a better feeling and a grasp of it, and we know what's to come in the future. So in the next video, we'll talk about delocalization, and we'll move on, and we'll go throughout the next part of the chapter in your text.